The next big idea we're going to talk about in the topic of circuits is the idea of electrical resistance. So electrical resistance defined is the hindrance to the flow of charge. And as we talked about before when we talked about current, that when an electron is trying to go across a wire, it does actually run into things. So the more collisions that it has, the more electrical resistance there is. So you have two competing ideas. You have an electric potential difference, which is voltage, which is trying to encourage the movement of charge. And then while the voltage is encouraging the charge to move, the resistance actually hinders it. So a couple different things that we'll look at here that affect electrical resistance. One is length. Again, thinking about the idea of collisions, the longer a wire is, the more collisions you're going to have, and therefore the more resistance there is. The next one is area. So cross-sectional area, I like to think about this in terms of a straw. So if you've ever tried to drink coffee or soda through one of those little coffee sticks, those little swizzle sticks, those little red ones, that it's really hard to get much liquid through the tiny little straws. But if you go over to McDonald's, I've noticed McDonald's has unusually wide straws. So you have a large cross-sectional area and you can get a lot more fluid through the McDonald's straw. So the same thing happens with electricity. If you have a skinny wire, it's just harder for the current to get through than if you have a fat wire. There's more room for that current to get through. So that's the idea with area. So you would actually have a good conductor if you could have a short fat wire would actually be a really good conductor. The third thing that we'll look at here is the idea of resistivity, and that is a property that different materials have that rates their ability to conduct electricity. So it depends on how it's made, its electronic structure, and it also depends on its temperature. For most things, you will find that the resistivity increases with increasing temperature, and actually it probably should say for conductors, the resistivity increases with temperature. So here you have a cold wire, and on the cold wire, the current's moving along. But when you get to a hot wire, if you think about kinetic molecular theory back from chemistry, the hotter a material gets, the more collisions that you have. So if you think about these little charges here bouncing around more, the more they bounce around, they're going to run into these electrons a lot more. So the hot wire actually will resist the flow of current more. The reason I said that's really true more for conductors is we talked about conductors having the idea of the sea of electrons. So electrons can move freely through the material because they have loosely bound electrons. The insulators, on the other hand, they have tightly bound electrons. So for a conductor, it's letting these electrons go through freely. If this were an insulator, it would be holding on to those electrons, and that's why it's a good insulator. So if you took an insulator and you heated it up, one thing you could actually do is you could actually jostle free some of those electrons. It's still not going to be a great conductor, but it has kind of the opposite effect. As far as this goes, though, think about this for conductors when we talk about resistivity, because there's really not a lot of point in rating the resistivity of an insulator. You're really talking more about wires, and you wouldn't make a wire out of something that is an insulator. So here's a couple numbers. You don't have to know any of these numbers, but just kind of get an idea of what they would look like for the resistivity of a bunch of different types of materials. So about the best resistor is silver, at least the best one on this chart, and you can see times 10 to the negative 8. We're talking about really small values. And notice that copper is actually not as good a resistor as silver. So, why don't you wire your house with silver wire? Most people have copper wires in their house. Well, obviously that would be a cost issue. If you were doing it purely on resistivity, you would use silver. But, unless you just really want to blow a whole bunch of money, that wouldn't make any sense. So silver being a precious metal, you don't use that. Copper, not as precious, although it does still have value. You've probably heard of people having their copper coils stolen out of their air conditioners. For a while, that was a big problem that people were having, and thieves were then selling the copper. But copper, compared to silver or gold, is still pretty darn inexpensive, and yet a very good conductor. So as we go down here, you have things with a larger resistivity value that are poor conductors, and you can see the order of magnitude changes drastically. The reason, by the way, there's a range here is that there's a whole bunch of different kinds of glass, so that's kind of a ballpark figure. And again, who's going to make a wire out of hard rubber? Terrible conductor. So That's just an idea on where some of those values fall. You don't ever have to memorize those. If I give you a resistivity problem, you'll either be given this constant or you'll be trying to find it, so you don't have to know them at all. Okay, so here's the equation that goes with resistivity. So you have the resistance that you could be calculating, you have the length of the wire, the area, and you have the resistivity. So that's what you use if you have to calculate resistance given a particular material. So here's an example of where you would see that. Determine the resistance of a 1 mile length of 12 gauge copper wire. They give that to you in kind of funny terms. I mean, actually, that's probably the way a layman would talk about it, but as far as problem solving in physics, you would need to know what a mile is in meters and what on earth is 12 gauge. 12 gauge actually refers to the diameter of the wire, so they're giving you that. So a mile is 1609 meters, and 12 gauge wire actually corresponds to this distance of this diameter in centimeters. And you may have heard of 14 gauge wire or some different gauge wire. If you go to Home Depot, you could probably buy it in terms of gauge. You wouldn't see that centimeter rating. And again, that's not something you would have to know, but that's kind of a helpful hint for Home Depot, I guess. So here's your equation for resistance with a resistivity value. The first thing you might want to know is we need both the resistivity value and we need the area, the length we already have. So to find the area, once we know the diameter, we can easily find the radius. So if we put that diameter in meters, divide it by 2, now we have the radius. Okay, it's not too bad. So then I go ahead and calculate the area. I put pi in there, square my radius, and then I have the area given here in meters squared. Okay, so now referring back to my equation, I need the resistivity. I can look back at that chart and find the resistivity for copper, and I've pasted it there. Now looking back at our equation, all we have to do is put those values in. So we have the resistance is the resistivity value times the length over the area. Okay, so we have all those values, you crank them in, and you get a resistance here of 7.8 ohms. And we'll talk more about the symbols for resistance on the next one. But that's just a few things about resistance. You won't see many of these problems at all, but more to see the definitions of resistivity and the variables that affect resistance in a material. That's it for this one.